A week before spring break too. Maybe that's maybe
yeah.
starting to get tiring. So,
Okay.
are we ready?
Yeah.
All right. Good. All right. So, in the talk that I had last time, I ended up on the circle rotation, and we were kind of talking about the dynamics behind this thing. So, what I wanted to do today was get into the doubling map and do that example, and then connect that back to how the doubling map was connected last time I discussed it, which is essentially a sequence. So let's talk a little bit about that. So we have this example here. So we take the so-called the doubling map, which is on the unit circle, and which again we identify with the unit interval 0, 1, and we identify the endpoints together. We just glue them together. So we take phi of x equal to 2x and then mod 1. And just recall that this map, if you write out the numbers in the interval 0, 1 in their binary expansion, then the only thing that this map does is it shifts the binary sequence to the left by 1. Okay, so phi takes binary sequence and it just shifts to the left by 1.
You're recording this?
It's going to be awesome to have in the background.
No. Actually, I had a joke, and it's like, okay, maybe the joke's not appropriate if they're actually recording this.
Right. So remember in the circle rotation case that we had, unless alpha was equal to 0, we had no fixed points. But in this case, we do have a fixed point. So those two systems are already kind of different, if you want to think of it like that. So in terms of dynamics, there is a fixed point at 0 here, because 0 is not going to be affected by the dynamics whatsoever. Okay, so we have that. So the circle rotation, the difference was that if our alpha was rational, then we got completely periodic behavior. And then if we change the alpha to an irrational, we had completely non-periodic behavior, but we got dense orbits. Okay, so just changing the map a little bit was different. Here, this time, we're not going to change the map at all, but we'll change the initial conditions. So the initial conditions are going to give us some different behavior depending on where we're at. Right? So again, think of the map as just a binary sequence and shifting it to the left by 1. Right? So we have some cases. Okay, so first let's just let x be rational. So even with the rational, we'll get, just by thinking of the rational as a binary sequence, so since we're in a rational here, the binary sequence, it's either going to be a finite sequence or it's going to be repetitive. And the place where the repetition happens is, of course, going to depend on the number. Okay, so for one, so if x can be represented with a finite number of zeros and ones, then if you apply the doubling map over and over and over as n goes to infinity, this thing is actually going to converge to the fixed point, and in fact it's going to do it in finite time. It's actually going to equal 0 at some n. Okay, so it actually, not only does it converge, but it actually equals for some n. So it'll actually go to 0. Okay. And the reason for that, and it'll do it, just depends on how many zeros and ones you need for that. Right? So if we can represent x's, and it's represented by, let's say, a string of zeros and one that has length maybe 10, then after you apply the map 10 times, all those sequences are going to eventually get killed off. And then you'll get nothing but zeros after, so that it'll just stay at the fixed point 0 for that. Okay? So if you can do it with a finite amount of zeros and ones, then everything's going to go to 0 for that. Okay? But if x is a repeating infinite sequence, then we either get a periodic orbit or an eventually periodic orbit. So we'll either have a finite bit of zeros and ones, or we'll either get some kind of repetition depending on somewhere. And the fact that we either get periodic or eventually periodic, it depends on where the repetition is happening. So if you immediately get repetition, so for instance, you kind of take an example of this, and you kind of have your sequences of zeros and ones are maybe 1, 0, 1, and then 1, 0, 1, 1, 0, 1, and then you go on for that forever, right? So we have repetition happening right at the beginning. Okay, it's the 1, 0, 1. So we have the repetition is length 3. So whenever we apply the map 3 times, this is going to shift over to the left 3 times, and we'll be right back at the 1, 0, 1. So this is going to end up giving you a periodic orbit of length 3, since repetition is immediate. Okay, so repetition is immediate. So it means it's periodic. Okay, now in the other case, you could have 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, and then we're going to start repeating 1, 0, 1, or do right here, 1, 0, 1, 1, 0, 1, 1, 0, 1, and then it repeats like that. Okay, so here's the repetition. Actually, I think I did actually repeat that more than I wanted to. 0, 1. Okay, so repetition looks like it happens. 1, 0, 1, 1, 0, 1, I mean, sorry. It's like it happens right here, right? So we have 1, 0, 1, 1, 0, 1, 1, 0, 1. So we're starting to repeat here. So there's no repetition here. So what we're going to have to do is the shift map, or the doubling map, is going to have to kill off all the beginning sequences first, or the beginning numbers of the sequence. But after it's done killing all that off, we get nothing but repetition after. So this one, we eventually get repetition. So that means we eventually get periodic behavior. So this is eventually periodic. Okay. So we get eventual repetition, which means we're eventually periodic. Okay, so as you can see here, not only do you get, depending on what type of repetition you have, you can get a period of any length that you want. Just repeat the sequence over however long of a period you want. So if you want a period of length 5, repeat it over the first 5, or pick whatever you want in the first 5 and then repeat that for the rest of the time after. If you want an eventual period of however length you want, then pick whatever you want in the beginning and then eventually just make everything start repeating. All right, so a period of any length can be attained for this. Okay, any questions on that? So what happens if it's irrational? And so since it's irrational, if you expand it using the binary sequence, there's no repetition. I mean, that's what an irrational number does. There's going to be no repetition in its expansion, so we get no periodic behavior whatsoever for this. So we can't even get any type of eventual period for this. So the expansion is non-repetitive, so no periodic behavior. So we get no periodic behavior whatsoever. Okay. So as far as periodicity is concerned, just from the simple fact of our initial condition x, where we choose it, we get completely different behavior. So you can kind of think of this as being chaotic. So there's a little bit of chaos in the system where the initial condition actually wildly affects everything. Okay. Now some cool things that actually come from this. Some of them are not too hard to actually show, but I'll go ahead and just list them out. So some cool little facts about this is that you can actually count. If you think of it in the sequences here, if you're asking for a period of a certain length, of any length n, you can actually count exactly how many periodic points of that length you have. And in fact, for any n, for any positive n, okay, there are, for each n and n, there are 2 to the n minus 1 periodic points of length n. Okay. So for each n, there are actually 2 to the n minus 1 periodic points of length n. If you want to think about intuitively how you can get something like that, it's really a counting argument from statistics or from probability. So for instance, if you want a period of length 3, okay, if you want a period of length 3, for instance, then just make your binary sequence repeat in the first, or pick whatever you want in the first 3, and then you just have to repeat that as the thing goes on, right? So in the first 3 slots here, okay, you could put 0 and 1, 0 and 1 in each slot. Okay. So you have 2 choices for each slot. You have 3 slots to choose from, right? So that gives you 8 choices altogether, 2 to the 3rd, right? So you have 2 to the 3 choices. Okay, now where's the minus 1 going to come from? Remember that we're dealing with S1, so recall that we identified 0 and 1, so 0 and 1 are essentially the same. So the only thing that's going to repeat is that, well, you can put zeros in the first 3 slots, but if you put 1s in the first 3 slots, you're going to repeat that forever, and that is just that's the binary expansion for 1, but 1 and 0 are the same here. So this 1 here is really not a new choice that you're getting. So this is why we're going to get 2 to the 3 minus 2 to the 3 choices, and then we have to subtract that by 1. So that's where the minus 1's coming from. Okay. So you can easily count them up like that just doing a combinatorial argument.
So how about length 4?
So if you want length 4?
Yeah, but you would have 1, 0, 1, 0. That's actually period 2. Right?
Period of length 4, 1, 0, 1, 0. Oh yeah. Sorry, yeah. So I'm abusing the I'm abusing the language a little bit, right? So I'm not saying for the periodic points that has to be the smallest. Okay, so yeah, let me make that distinction. That's a good point. So it's not necessarily the smallest period. So you can get periodic behavior, and of course your example shows that you get a period of 2 for that, right? So yeah. So but if you want it to repeat over however length that you want, then you kind of think of it like that. All right. So the other thing too that you get, it's going to deal with a little bit of topology for the other 2, but I figured they're worth mentioning anyway. The periodic points are actually dense. And the other thing is that there actually is a dense orbit. Okay, so there exists a dense orbit. Okay, so you can orbit there is a dense orbit of some element in there. Okay, and you can do this. It does actually use a little bit of symbolics in order to do that. Okay, but these are kind of some nice little facts about this system to get a little bit of the dynamics that go behind it. Okay.
So the dense orbit must be irrational, right?
Yeah, for sure. Okay, and it's knowing a little bit about symbolic dynamics. Actually, you can build it. You can build it yourself, and this is kind of like, I haven't really told you what it is, but you can build the dense orbit yourself, and of course, it's going to be an irrational thing. All right, are there any questions on any of this? All right, good deal. So those are really the examples I wanted to talk about as far as dynamics is concerned. The last few things I want to do with the time that I have left, at least do a little bit of dynamics and a little bit of symbolics. First, I just want to briefly discuss how you can compare 2 different dynamical systems. And I want to show you a little bit, or at least a general idea on how you can use this idea of using a sequence to kind of help you represent any dynamical system that you want. Okay. So for one, how do we compare two dynamical systems? Okay, so let me just list out some of the things that you can do to compare two things. Okay, so the idea, if you want to compare two dynamical systems, you're really dealing with two different phase spaces, but you're also dealing with two different dynamics. So there's two things that you really have to consider. You have to consider the space, and then you have to consider the continuous map. So there has to be some kind of interplay between both of them. And so we formulate the definition if you want to compare two together. And the idea of comparing two together is that, well, if we have two dynamical systems, if we think about it in a topological sense, since we're talking about continuity, and since our map is only assumed to be continuous, how can we tell whenever two systems are really doing the same thing? Are really, their dynamics are really doing the same thing, even though the maps are made look different. Okay? So this kind of gives some, a motivation for this definition. So if you're given two dynamical systems, call them M and Phi, and we'll do N and Psi. Let's say a homomorphism. It's a little bit of abuse from a ton of other things that use the word homomorphism. But a homomorphism will denote a theta. It's going to go from M to N. Okay? It's just a continuous map. Okay? So it's a continuous function that kind of relates M and N together. Okay, but again, we need some kind of interplay between the maps Phi and Psi. Okay, so how can we get that interplay between that? So such that we have this additional thing. Kind of have this little conversion between the two. So if we take Psi and compose it with theta, it's the same thing as theta composed with Phi. Right, so essentially the picture is, this is just, if you kind of draw this out as a diagram, right, we have two different systems, M and N. The dynamics, well, that's going to act on M itself. So if we go by Phi, we'll get something that will land back in M. The dynamics operates on N, so anything acting on Psi is going to land back in N. And we have this connection between the two. So all it's telling you is that if you apply theta first and then psi, it's the same thing as just applying phi first and then theta. Okay, so it's just a commutative diagram. That's all it's saying. Okay, so this is just a commutative thing. So there's some kind of relationship between the two systems and their dynamics. All right, so depending on the condition that you put on theta, will help at least keep some things intact, or at least help your structure out a little bit. Okay, so if theta is 1 to 1, we say theta is an embedding. If theta is on 2, or surjective, we say theta is a factor map. And then if it's both, if it's 1 to 1 and on 2,
Thank you.
so if it's 1 to 1 and on 2 with a continuous inverse, so in a topological sense it's a homeomorphism. But in the dynamic sense, we'll call this a conjugacy, or a topological conjugacy. Okay, so all three of them in their own little right are kind of nice things to have if you have that additional structure on theta. The one that's really, the ones that a lot of dynamicists think about as a topological conjugacy, that's kind of our way to tell if two systems are really the same or not. Now keep in mind that this may not tell you exactly everything in the system is the same. This is just, the theta here is a continuous inverse, it's 1-to-1 and on 2. All right, so it'll preserve anything you can say topologically about your space. Okay, so I'll make a note about things that are preserved between the systems, and the proofs of them are really not are not hard at all. So I'll just leave them out for here. But what that says is a lot of things that you can say about your open system, about open sets and M&N, are just preserved by that if you have a topological conjugacy. So the main idea is, how do you tell when two systems are conjugate? Or how do you tell when they're really the same? Okay? Now, in general, that's an intensely difficult question to ask, just like any type of classification question that you can ask in groups. It's hard how to tell if two groups are isomorphic. Well, it's really hard to do any of that. So we try to find things that are invariant under topological conjugacy, or things that are just preserved. Okay? So this is how you can tell with those, right? So let me just list out things that are preserved under topological conjugacy to kind of give you a way to think about how you can think of two systems being the same, or how you can distinguish between two. Right? So invariance of a topological conjugacy. Right, so what things are preserved whenever you have a topological conjugacy? Well, one thing are the periodic points and fixed points. Those are definitely two things that are always going to be preserved in that. So fixed points is one, and periodic points.
Is it sufficient to show that you have a topological conjugacy if you have those two only?
If you have those two only, oh no, not at all. So
No.
if the fixed points and the periodic points are preserved,
Is it sufficient?
no, I don't. I know.
Oh.
No. There's other. I mean, if these are the only two things that you really need to tell if they were different or not,
Yeah.
or if they were the same, then that, we wouldn't have to do too much work for that.
Okay.
I think so. No, those are definitely not going to be the only things.
Okay.
All right, so fixed point and periodic points will be preserved. If you have a conjugacy, this will follow just from the fact that you can just use, all it really does is just use the definition. That's all you really need for it. And the fact that in a conjugacy, that map theta that you have is 1-to-1 and onto, so it's a bijection. So everything's going to be nicely preserved for that. So if you have two systems and you're comparing them, if their number of fixed points are different, then that's enough to tell that they're different, that the dynamics of the system are really different. Same thing for periodic points. The second thing is something that I mentioned in one of the problems, but I didn't give it actual definition. It's called topological transitivity. All right, so what that tells you, just really quick definition for it. So for any two open sets, U and V, there exists an N such that phi n of U intersect V is not empty. So it just happens for one N. So it essentially tells you that it takes kind of every open set and it moves it around the space enough to where it eventually intersects everything else in the set. Right? So it eventually kind of sees everything else in your space M or N, depending on where you work. Right? So it preserves that. So again, this is kind of something, this is a statement about open sets, so a topological conjugacy is going to preserve things like this. And then a stronger form, kind of if you want to think about this next thing, it's really like a really strong form of topological transitivity. It's called topological mixing. It's essentially the same definition, but it kind of, this definition is going to hold for every N after a certain threshold. So it's like, the dynamics is going to move an open set to pretty much kind of chop it up and put it in every other open set in the space after a certain number of iterates. All right, so let me make that precise. So for each pair of open sets, U and V, there exists an N naught such that phi n of u intersects v non-trivially, or just it actually intersects it, intersects v for all n greater than or equal to that n naught. Right? So this is a stronger form of this. Topological transitivity, it's going to eventually move it to every other open set, but it can move it away, right? So it can keep traveling everywhere else. Topological mixing is telling us that after it reaches a certain threshold n naught, this intersection is going to stay true no matter what, no matter how far away you go into the dynamics, right? So the mixing thing kind of tells you that it takes kind of all your sets and it just mixes them all around, kind of like equally distributes them, if you want to think of it like that. Kind of distributes them to different parts of the set and it'll stay there the whole time. So these are kind of some basic things that'll always stay true if you have a topological conjugacy. So these are some things that you can help determine if your two systems are really the same or not. So for one, the circle rotation and the doubling map, those two things are automatically not topologically conjugate, or they're not the same, just from the fixed point problem, right? As long as alpha wasn't 0, the circle rotation had no fixed points, but the doubling map had that fixed point at 0. So those two things are not going to be the same. Okay, so that's essentially all I wanted to say about how to compare two dynamical systems. So are there any questions for that? All right, so for the last little bit here that I'm going to do, I'm going to kind of describe symbolic dynamics, kind of apply the stuff with the sequences, and how you can kind of use the sequences to help describe a little bit of your dynamical systems. If you think about sequences, like you said, the periodic, or like we had seen before, the periodicity and all that stuff is really easy to determine if you're just thinking about things in terms of sequences. So how can we do this maybe construction in general? So let's do a little bit of things that can be described symbolically are very easy and very nice to understand. Right? So how can we take not every dynamical system is going to be a shift space. Like that map just happened to be very nice, and we thought about it in binary sequences, where it turned out to be the shift map. But not everything is exactly a shifting of some sequence or anything. So in general, the dynamics could be way more complicated than that, right? But there is some kind of way where we can think about maybe splitting our space up into different sets and then thinking about things in terms of shifting. We may lose a little bit of information doing that, but we actually do retain some of the other information in the system, and we can tell some things about that, right? So here's the construction of that. So I'll tell you the construction of the shift space. I'm going to put quotes around that because I think the word shift space actually means something in symbolics, but I'll call it a shift space. The terminology shift space I'll use is we're talking about sequences, and the map we have is a shifting map where we just shift sequences to the left. Right? So what we're going to do is we start off. We start off with some set A. It's a finite set. It could be a set of anything, doesn't really matter. For convenience, I'll take it to be a set of numbers. So I'll do 1, 2, 3, all the way up to n. Right. I should probably start at 0. Let's start at 0. And then we just go to n minus 1. So it's a set that has n elements in it. Okay. And so in order to talk about the dynamics, again, we need to talk about some kind of continuous function. We need to talk about maybe some kind of metric space or some kind of topological space. So what we're going to do is we're going to equip A with the discrete topology. So this is where some of the topological things are going to start coming in. And so recall that the discrete topology just means that every subset of A is open. We just classify everything in A as an open set. So the topology on A that we have here is just the power set. So everything here is going to be open. So we're going to equip A with the discrete topology. Now, since it's a finite set, and equipping it with the discrete topology, right, so if you think of compactness again as every open cover has a finite subcover, under the discrete topology, this is going to be a compact set. Right, so this is going to be a compact space. So everything's looking good so far. So notice that A is a compact space. Okay, so you can think of A, we're going to be building sequences, and the A is going to be the types of symbols we can use in our sequences. So you can kind of think about this as your alphabet. This is the alphabet that we're going to allow in the sequence. So in the binary sequences, the set A is kind of considered just to be 0 and 1. Those are the only numbers, or the only symbols we're allowed to use here. So what we're going to do is that in order to build sequences, we're just going to take a product of sets of A. Right? So we're going to take some infinite products. So what we're going to do is we're going to let our set X be this infinite product, and we're going to range over Z. And what we're going to do is we're going to take countable amount of copies, products of just this set here. Okay, so we're taking this product space, and what we're going to do is we're going to equip it we can equip this thing with the product topology. All right, and remember the reason why we can, one of the good reasons why we want to equip it with the product topology is thinking back to my first lecture. These A's are compact spaces with the discrete topology. So taking any type of product that you want, it could be uncountable if you want, but we're just doing this over Z. Taking a countable product of compact spaces and the product topology is still going to be compact. Right? So that's by Tikhonov's theorem, just to remind you of that. So here we have that X is compact. This is by Tikhanov. And with the product there, really all X is just a sequence space. That's all it is. So the elements in X are kind of this infinite tuple in both directions, right? So we're just getting elements in X just look like sequences. So you can really think of X as really the space of all sequences AI. I can range over Z, such that each AI comes from your set A. So it's just this infinite sequence in both directions, and each thing in the sequence is coming from A. So we have our compact space. This is really what the elements look like, so they're really sequences. Now the last thing, I kind of defined a dynamical system as a metric space coupled with a continuous function. So what's the metric that you can put on this thing? All right, so there are actually a lot of different metrics that you can do. So the one metric that you can do is kind of nice and easy. This is the metric that we can do that. So we can take the distance between any 2 points. We're going to define it as 2 to the negative k, and I'll describe what the k is going to mean in a second. So k, what that's going to do is that the distance between any 2 sequences in the space is going to be 2 to the negative k, where k is the maximal, kind of the maximal index, if you want, or integer. In this case, it's going to be an integer. And in fact, it's going to be a positive integer. For this, it's going to be the maximal index where the sequences match up exactly over indices I that are in the closed interval negative k to k. So essentially all you do is that you compare 2 sequences together. So kind of give you a picture here. So we're going to have x in the -3, x in the -2, x in the -1, x0, x1, x2, x3. We go infinite in both directions, and then we take another sequence. Y -2, y -3, y -2, y-1, y0, y1, y2, y3. And what you do, what the metric is kind of telling you to do, or one thing you can do in order to calculate the distance between 2 points, is that you go to the first symbol there, x0 and y0, and you compare them. If those two things are the same, then you move one in both directions and compare those two things together. So we're going to move, if these two things are the same, then we move to the left and right, and we compare kind of this space in the sequence. So we compare that. If those two sequences match up on there, then you keep moving further and further away and keep going about that. Right? And you keep doing that until you reach a spot where they're not the same anymore. Okay? So for instance, if x0 and y0 are not equal to each other right off the bat, then k is going to be 0, and the metric is going to be equal to 1. So we say that they're distance 1 apart. If it ends up being the fact that x0 are the same, but whenever you move to this space here, and if there's anything in those two sequences that don't match up, then the metric here is going to be, well, it's going to be 2 to the negative 1.
So how do you choose x, 0, y, 0?
What's that? I'm sorry?
I mean, since it's integers, not just positive, you can like actually choose any point, any number.
Yeah. So
with 0.
Yeah. So the kind of the ambiguity here is that you kind of have to define. You have to define like where's your beginning sequence, right? Yeah, you have to define where this x0 is. And usually what they do, or usually the idea to do that is that if you want to define like where your beginning of your sequence is, or they usually put like a decimal point, kind of like you would in like base 10 or something, to kind of indicate maybe where your x0 is going to be, right? So there's a little, since you're going in both directions, of course, you have to indicate where the beginning of your sequence is. This has to be established, right?
I have a question also.
Yeah, sure.
If, for example, x0, y0 are the same,
Yeah.
but x1 and the others are not, just x1 and y1.
Yeah.
How do you continue that? You continue from the right?
No, you continue. You continue. Like, how do you continue to keep going?
Yeah, keep going.
So you just go, right? You go equal in both directions, right?
Okay.
So if x0 and y0 are not the same, there's nowhere else to go. You know where your metric is, right? But if they are the same, you go one spot each way, right? So it's over like equal.
Okay.
You're going over like equal lengths each way, right? So you move and you keep going. You keep going until you're kind of running into a spot where they just don't match up anymore.
Okay.
Right, and wherever that happens, wherever they don't match up is going to be where.
Okay.
All right, so that's the idea behind the metric in there. So this is the space that we're working over. Here's the metric. It's compact. We have a compact space. It's a metric space. And so the map that we're going to have here, so the continuous map, that can help kind of describe your dynamics in the shift space, is going to be, well, the nice map that we had in the doubling map, which is the shift map. So it's going to be the shift map. So the shift map, you just denote by sigma. It's going to go from x to x. Okay. And all it does is it just takes a sequence. Let's write it in words, figured it'd be better. So it takes a sequence and shifts the sequence to the left